recap of what we did in class today. First of all, you have 3 things to do for homework. Vote, vote, vote. Remember to vote. I'll put the link down at the bottom, but you should all have it. Vote. Let's get SDJLI way up top. Work on corrections. You have tons of corrections to work on, not just the ones I handed back today, the test I handed back today, but look at old work and see if there's any corrections you can make. Also, please watch the 7.1 video, which is going to go online tonight in the YouTube channel. I'll also put the link to it as many places as I can. Check the Twitter feed too. So I want to give you a preview of what to expect, what's coming up. We have a few things coming up. We have to do Unit 7. We have to do a Unit 7 test. We have to do our final. And then we have to do the department exam. There's a lot to get through, but you guys are going to slam it and do really, really well. So 7.1, an overview, is solving linear systems by hand, by graphing. So what a linear system is multiple equations that you're trying to find a solution that works in both equations. So you have 2 equations with x's and y's. They're going to be linear, so they are going to be lines, and you're going to graph both of them. Now, each graph represents all of the possible solutions to line 1 are right there. All of the solutions to line 2 are right there. So where they intersect, that point will be a solution to both. It's important to note that this is not 100% accurate, because you're going to be looking at your graph and guessing where the point of intersection is. Sometimes it'll work really, really nicely. Sometimes it might be off a little bit. You also need to remember that there are 3 types of lines that we could be working with: slope-intercept, standard form, or lines written in point-slope form. So you're going to have multiple equations, and you're looking for the point that works in both equations. You're going to do that by graphing. The second topic we're going to look at in Unit 7 is solving linear systems with algebra. What's nice is that you get exact answers. If you do everything correctly, you get a perfect answer. The primary method we're going to be using is substitution, where we have multiple equations. We're going to isolate a variable and substitute. Again, this is exact, so in the future, it's probably going to be the one you're going to use most often because it's exact. Graphing you're going to do when you have no other means. Solving systems algebraically is what you're going to do when you can actually figure out the algebra. Direct variation is its own topic, but it's really, really straightforward. It represents a line. Direct variation are 2 things that relate linearly and pass through the origin. So how many different lines can pass through the origin? Well, an infinite number of them can. Like, here's another one. There's another one you could draw like this. So it gets its own category, but it's pretty straightforward. The only thing that's important to remember about direct variation is that all the lines have the form y equals k times x, where in this case k is the slope. They're just relabeling it. It's kind of arbitrary. I don't know why it's k, but when you see y equals kx, it means direct variation. That's what it means. We've already looked at perpendicular and parallel lines in detail. We're going to re-examine them in a little bit more depth, but it's important to remember that parallel lines have, this is the symbol for parallel, have two parallel lines have the same slope and they never touch. 2 lines that are perpendicular, and this is the symbol for perpendicular, the upside down T. One has the slope a over b, the other one has the slope negative b over a. The phrase you're looking for to remember is opposite reciprocal. Reciprocal. Opposite reciprocal slopes. And the easiest way to remember that is when you multiply the slopes together, they multiply together to get -1. Now we have that big question we've been working on. We might come back to it and incorporate some more perpendicular and parallel line stuff. Piecewise defined functions are going to be functions that look like this. They could be curvy. They could also be straight. But the new thing that's going to be introduced is these piecewise functions can have gaps. The thing to remember about piecewise functions is that they are functions that are defined in pieces. That's it, in pieces. In the classical example is movie prices. If you're maybe 0 to 5, the cost might be, let's say, $3 to get into a movie. From 6 to 12, it might be $5 to get into a movie. And then 12 plus might be $8 to get into a movie. Those numbers don't change between 0 and 5 or 6 to 12 or 12 and up, but it's a different function for each piece. There are many piecewise defined occurrences in real life. We're going to look at many of them. We will look at graphing linear inequalities. That's where you have one line gets drawn and you determine which side of the line you're going to shade. You then graph a second line. You determine which side of the line you're going to shade. You're then going to figure out where they overlap and you're going to answer a question based on the region where they overlap. So you need to be able to graph, you need to be able to pick which side of the line to shade, and then you need to be able to shade in two places without going berserk. 7.7, the last topic we're going to cover is function composition. You've mainly seen functions that look like this, where you go from one output, goes into the function, and it pumps out, one input gets pumped into the function, and you get one output. What we're going to do is we're going to add a bridging function where you're going to plug an input into f, then this value is going to get thrown into a second function g, and then you're going to get a final output here. We're not going to call it z, but this is the output, this is the input. What does it look like mathematically? Well, let's say we had the function f of x, and we wanted to do f of 7. F of 7 is 7 plus 2, which is 9. We're then going to plug 9 into g of x, so g of 9 is going in right there, and that equals 2 times 9, which is 18, minus 3 is 15. So what we've just done is we've evaluated f at 9, and then we've plugged that into g, and we found out that g of f of 9 is 15. Seems strange? This is just what it looks like, and this is just meant as a preview. So tonight, make sure you vote, watch 7.1, and you will watch this video right here. Have a good night, everybody.